Hello, young physicists. Have you ever wondered what's hiding inside the tiny nucleus of an atom? It's like a secret clubhouse where the real action happens. Here's a fun thought: why don't atoms ever get lost? Because they always have a nucleus to guide them. Now, nuclear physics is the branch that investigates just that, the constituents and structure of the nucleus, and what holds it all together. Imagine the atom as a solar system, but with a twist. The nucleus, a dense ball made of protons and neutrons, sits right at the center, while tiny electrons whirl around it. But get this, the nuclear radius is tiny, about 1 × 10⁻⁻15 meters. That's unimaginably small. Despite this minuscule size, the nucleus packs nearly the entire mass of the atom. To put it simply, if an atom were a huge stadium, its nucleus would be a marble on the field, but that marble would still hold almost all the players. The nuclear density is insanely high, around 10⁻17 kilograms per cubic meter, denser than anything we encounter daily. The number of protons, denoted by Z, defines the atomic number, essentially the atom's identity card, while the total number of nucleons, which means protons plus neutrons and is written as A, defines the mass number. So Z tells you who the atom is, and it tells you how much it weighs. This is the playground of nuclear physics, where understanding these tiny, dense centers leads to big discoveries for energy, medicine, and beyond. Let's dive deeper into what makes up the nucleus and how we describe it. Every nucleus can be identified by two numbers: the mass number, labeled A, which counts all the protons plus neutrons, and the atomic number, labeled Z, which counts just the protons. The number of neutrons is simply the difference between the two, that is, N equals a minus Z. Now, here's where things get interesting with terms you might have heard: isotopes, isobars, and isotones. Isotopes share the same atomic number Z, meaning the same type of element, but have different mass numbers A. That's like having siblings who wear the same team jersey but weigh differently. Isobars, on the other hand, have the same mass number A but different atomic numbers Z. Think of cousins who weigh the same but cheer for different teams. And then isotones have the same number of neutrons, regardless of their protons. For example, carbon-14, written as carbon with mass number 14 and atomic number 6, and nitrogen-14, nitrogen with mass number 14 and atomic number 7, are isobars. They both weigh the same but have different charges. Now, to hold all these nucleons tightly together, the nucleus relies on nuclear forces, strong, short-range interactions that work like an invisible glue. These forces don't care about electric charge, they treat protons and neutrons alike. Plus, they are saturating, meaning each nucleon only feels the tug from its nearest neighbors, just like how each friend in a crowd only pulls on those right next to them at a tug-of-war. How big is a nucleus? Well, that's where empirical laws save the day. The nuclear radius R can be approximated by the formula: R equals R naught multiplied by A to the power of 1/3, where R naught is about 1.2 × 10⁻⁻15 meters. What does this mean? As the total number of nucleons A increases, the radius grows, but not linearly. It grows with the cube root, so bigger nuclei aren't just bigger in all directions, they follow a specific scale. Imagine stacking tiny spheres inside a larger sphere. The volume of a nucleus, which is proportional to the cube of the radius, actually increases directly with A. This tells us the nuclear matter is almost incompressible. Adding a nucleon increases the total volume, but the density stays constant. Speaking of density, typical nuclear density can be calculated using the formula: density equals A times m sub n, that's the neutron mass, divided by 4/3 times pi times r cubed. Because the radius scales as a to the 1/3 power, when you cube it in the denominator, the a cancels out, leaving density as approximately constant for all nuclei. So whether you're looking at the tiny nucleus of helium or the massive nucleus of uranium, the density remains staggeringly high and nearly the same, about 1 × 10⁻17 kilograms per cubic meter, which is millions of times denser than normal matter around us. Now, let's explore the fascinating concept of mass defect and binding energy, the superheroes behind nuclear stability. When we add up the masses of individual protons and neutrons that make up a nucleus, their total exceeds the actual mass of the nucleus. This difference is called the mass defect, delta M, which equals Z times M sub P, the proton mass, plus N times M sub N, the neutron mass, minus M, the actual nuclear mass. Why does this happen? Because some mass gets converted into energy to hold the nucleus together. This energy, called binding energy, is given by the formula E sub B equals delta M multiplied by c², where c is the speed of light in meters per second. Binding energy represents the amount of energy you'd need to break the nucleus into individual protons and neutrons. The more binding energy per nucleon, that's E sub B divided by A, the more stable the nucleus is. For example, iron 56 has one of the highest binding energy per nucleon, making it one of the most stable nuclei in the universe. It's like the perfect sturdy Lego structure. The bricks stick together so well that it takes more effort to pull them apart. This principle underpins everything from stellar energy to nuclear reactors, showing us how mass converts directly to enormous energy. Let's wrap up the key ideas we covered about the nucleus. Remember, the nuclear radius R equals R naught multiplied by a to the 1/3 power, with R naught around 1.2 × 10⁻15 meters, telling us that size grows with the cube root of mass number. The nuclear density, calculated as a times neutron mass divided by 4/3 pi times radius cubed, remains nearly constant across different nuclei, showing nuclear matter's amazing incompressibility. The binding energy E sub B equals open bracket Z times proton mass plus N times neutron mass minus the nuclear mass close bracket multiplied by c², illustrating mass defect transforming into energy that binds nucleons tightly. So, in essence, nuclear physics studies these tiny, dense centers of atoms, revealing the forces and energy that make them stable. These insights are crucial not only for understanding the universe but also for amazing applications like energy production and medical technology. That's it for today's introduction to nuclear physics. Remember, physics is even more fun when you can understand the secrets hidden in the tiniest parts of nature. See you in the next session.